Artem, you want to do an introduction for this reboot of IREE community meetings?
Yeah, sure. First of all, yeah, thanks, Jakob, for setting this up for us, and thanks, Abdel, for agreeing to present today. This is the second meeting in the series. First one already hosted in March. So today is the reboot of Tech Talks, I guess, in this kind of format. And Abdel Younes from Synaptics is here today to talk us, all of us, through the Torq compiler suite and how IREE is employed there. Yeah, I think Abdel will be the best person to actually describe the details of it. But yeah, thanks everyone for joining, and hope that it goes.
Thanks, Artem. So my name is Abdel Younes. I work for Synaptics, based in Switzerland. So we have quite some people today working on this Torq compiler suite. So Torq is a new NPU design from Synaptics, which we already integrated in one SoC, the SL2610 SoC. So we started from scratch the development of this Torq compiler, and very early on we decided to use MLIR, and naturally IREE came as the best framework to start this development. Actually, from an historical point of view, we started thanks to Max, who is in the call now, from Roofline. He gave us, none of us knew about MLIR, none of us knew about IREE. So we knew about AI and Edge AI and some of the compiler. We had SoC with VeriSilicon NPU before. So we had a toolkit and a compiler that was working quite nicely, but we started this from scratch. So after a few months of training and study, we started, and we basically 2 years later we have now a compiler suite which is working and supports a real life SoC. Okay, so this Torq design, I'm going to describe very briefly the hardware, and then I will go on to the software, what we have, overall architecture, the feature, and some of the tools that we have developed along this Torq compiler, and I will talk about the future. If anybody wants to ask question, for me it's fine to stop and address any question during the presentation. So the Torq NPU is composed of multiple components. So we have the NPU component. So basically we have a system DMA with high bandwidth local memory, 512 kilobytes of SRAM. We have two compute engines that can work in parallel. Each of those can support 256 int8 MAC or 64 BF16 MAC. This LU engine, I'm not going into the detail, but so it's a standard multiply and accumulate engine, but it has a lot more feature, like a lot of activation capabilities. It can do more stuff than just multiply and accumulate. So those two engines can communicate, can read and write from this local RAM. And then we have this Coral NPU, which we call internally the CSS, as for CPU subsystem. It's basically, in this first iteration, a RISC-V processor, integer only in this first version. I will talk a bit about the next version in the next SoC later. So it's a RISC-V subsystem with 2 memory bank, ITCM 8 kilobyte for the instruction set, and DTCM 32 kilobyte for the data. So this Torq IP is connected through an AXI bus to the main SoC memory controller and the DDR. So with those 2 Mac engine, we can support up to 1 TOPS. As I said, we natively support int8 and bfloat 16. int16 is can be done using int8 arithmetics. So we can support any kind of neural network or transformers today. It's so we developed the Torq compiler based on IREE, and the goal is eventually to support any model through the decomposition of any operation into instruction that can be executed by the hardware, either the Mac part, the NSS part, the NPU part, or the Coral NPU part, or even the host. So we are building a heterogeneous compiler and inference system. Okay, so for this development, we are partnering with Google Research. So Google engineers are actively participating to the development of the Torq compiler. We can support now PyTorch input, PyTorch model, LiteRT or TF-Lite, JAX, and ONNX. I mean, we can also support Keras through LiteRT today. First version in the 2610 is V1, which pairs with Coral NPU V1. As I said, it's a plain RISC-V 32-bit core. Next version, T2, will have will embed the Coral NPU V2, which will support floating point operation and RVV extension, so 128-bit vector capabilities. And then next version will pair with next version of Coral NPU. So this is a diagram of the flow between the high-level model format to something that can run on the device. So we start from those high-level format, PyTorch, ONNX, JAX, TF-Lite, LiteRT. We have some importers. So that's mostly the standard IREE flow. We have some, we built some script and some support for high-level stuff like JAX and Keras. But other than that, it's really standard IREE. So we import that into a number of dialects. Today we support Torch, ONNX, MNIR, Tablet or TOSA, same as IREE, really. We lower that to using those subcomponents to either linear, tensor, math, array, etc., which then can transform into our own dialect, which we call Torq HL. HL as in high level. So that's for the operation that we can execute in the Mac engine on the so-called NSS network subsystem. We can, for those operations that we cannot support today, we have an automatic fallback to the Coral NPU, so which we call CSS, as in computer subsystem. And we are using the plain LLVM IR and the LLVM CPU backend, which generate for us the RISC-V bytecode. As a second fallback, we can use host, that is the ARM CPU that is in the SL2610. Eventually, we don't do that yet, but the SL2610 has a GPU, a small GPU, which we can use probably to generate, to use the GPU as a compute engine. Then we have the serialization. So we generate a single VFMB, so single compiled model, which can run heterogeneously on the NSS, so the Torq T1 by Torq T1 AP, or the CSS, the Coral NPU, or the host, and eventually in the future, the GPU. And then we can deploy that to the Astra SoC. Today, we have many examples, a computer vision example, or LLMs, or speech to text. So this is a completely open source and open development. So we have our internal GitHub repo, which is private, but the history that is published regularly in this public GitHub project is the same as the internal history. The reason why we keep private our development is because we track a number of customer tickets, which we don't want to be public. So the Torq compiler actually is an IREE plugin. In order to make it easy to compile and integrate, we chose to embed IREE as a Git submodule today. Might change in the future, but it turns out that it is quite well integrated. So we have a CMake subsystem, which we'll call the IREE CMake subsystem, and we set up the default what we need for our project. So we maintain a few fork, a fork of IREE, a fork of LLVM project for MLIR, and also Torch MLIR, because we need some patches for a number of models that we are maintaining. In parallel to this Torq compiler, we have Torq Tools GitHub project, which is a collection of tools for model optimization and preparation for Torq. So today, for example, for Moonshine or for Gemma-Free or for other stuff, we are using this Torq tool repository, which to basically prepare the model for it. It's mostly about ONNX. For example, we have a conversion tool from FP32 to BF16. We have tool to convert a dynamic KV cache, for example, in Moonshine to static KV cache, this kind of stuff. And then we have, for users, this Torq example Git, which contain a number of AI demo. Today, it's mostly Gemma-free, but we want to put more demo in there for Moonshine, YOLO V8, and anything that is relevant to our marketing and sales team, basically. Roadmap. So we are settled on a bi-monthly release. Today, the current release is v15.1. It's based on the quite old IREE code base from July 2024. This release was branched out in order to support our Astra SDK, which is the Yocto SDK that we maintain for our SoCs, including the SL2610 SoC. The idea is that for each of those releases, we will continue, we will support with bug fixes mostly, until the next release. So V151 will be, the V15 branch, sorry, will be supported until at least the release of V2, which will happen end of May. So this V151 already support quite a lot of, not a lot, quite a number of models, including MobileNet V2, ResNet, EfficientNet, YOLO V8 pose detection or object detection. We support also Moonshine, support an LLM, so small LM2. The next version will be a big upgrade. So we manage through a lot of effort to rebase the development to IREE 3.10. We are progressing quite significantly with our tiling algorithm, which we call Tile Infuse. We are developing a new, so let's say that our compiler is not able to compile everything yet, right? So we developed a new tool, which we call the Executor Discovery tool, which runs on top of the compiler and will prepare the model for iteration. We'll try different paths, so either pure hardware or CSS, Coral, or host, and decide that ahead of time in order to support any model. So we will support, we are already supporting Gemma 3, so Google Gemma 3. We want to show that a demo of that very soon. And we also integrated StableHLO input in this release. And then we will have the V10 end of July, which I hope will be based on latest IREE, and maybe we'll create an option to build against the latest main branch. So in order to track the development and make sure that we don't face any regression. We will try also to upstream our patches for IREE MLIR and Torq MLIR. So I'm not going into the details of all those patches, but we accumulated quite a few, which may be of interest to the community. So we want, of course, to have more robustness and performance. And of course, the idea is that we will support current Torq T1 and upcoming Torq T2 in this release. So as part of the Torq compiler, we developed quite nice testing framework based on PyTest. We are not today using much the MLIR IREE testing framework. We develop on our own for a number of reasons, for caching, for it's quite elaborate. We have end-to-end testing and single operation testing. Our test framework can work with high-level format like TF-Lite, 1NX, or Keras, but also pure MLIR like LinAlg or TOSA or StableHLO. So we automate the conversion, all the conversion that are needed to compile and run the test cases that we support. So we import to MLIR, we execute the Torq compiler, we execute the Torq runtime through simulation. And then if it passes, we can compile and execute for FPGA or the SL2610 board. Yes?
Abdel, I wanted to ask about the reference path for this testing framework. Do you and your team or Synaptics as a whole also work on execution providers, let's say for Onyx, for the Torq hardware, and for the whole ecosystem? And like, do you actively optimize them further and kind of compare still against the IREE development path, or is it more just the reference that is known to be well optimized?
So for the MLIR test case, our reference is quite often the LLVM CPU bucket. But more and more, we are using other engine as the reference. For example, it can be TF-Lite runtime, LiteRT runtime, or ONNX runtime. We just integrated in the latest main support for PyTorch runtime as well. So the idea is that we would like to define more and more tests in high-level language like Keras or PyTorch or JAX rather than in MLIR. So we integrate those reference, but we don't modify them. We just our framework is just pip install the various runtime that we need.
So the comparison is for more so for accuracy and
Yes.
other correctness metrics than for performance.
Yes, yes. For simulation, we don't care much about performance. Of course, we want to be fast, but simulation is quite slow compared to actual, but it runs well. So we have something like 3,000 test cases, and we run all of them in simulation first. Yeah.
Understood. Thank you.
Okay. So we have those small test cases where we compare the result of either the high-level runtime or the LLVM CPU output with our own Torq inference, Torq runtime outputs. For some of them, actually, and this might be interesting for the community, we have accuracy issue. For example, for resize nearest neighbor, we found out that LLVM CPU backend is not accurate, and our output is close to the TF-Lite. So we have this kind of accuracy issue on a number of tests, also for some matmul, where LLVM CPU doesn't give the exact same result as as TF-Lite or PyTorch. Yeah. So so for the end-to-end testing, we have also the ability to integrate a reference input, which can be an image, a sound, or a random tensor, to pre-process it, and then we can also post-process optionally. For example, in the case of classification or object detection, we will do the post-processing that we need, and the comparison will be really on the model result and not on the raw outputs. Okay, so we have a test plan that we have a number of test plans that we run on GitHub with the help of some AWS server. We have a dashboard which is quite nifty, but is showing all the results for all the pull requests that we have, and also the two main branches, so main and v15. We can track the number of tests, the number of X-fail, because we still have quite a number of test cases that are not compiling. We try to decrease that, but we have a system that will track, but we try to track the known failures, and the idea is that those known failures will decrease over time. So just to show you some screenshot of how dashboard, I can also show you that live, but this is not public. We are thinking maybe that it would make sense to have a public version of this dashboard at some point. But for now, it's costing us a lot of resources. It's a lot of development, so we focus on our internal development. Maybe later we'll have a public dashboard. So with this dashboard, we can have, for example, this is for MBV2. We can track the performance over time. So here we're talking about 50 milliseconds, but this is on FPGA. FPGA run at 100 megahertz. So you have to divide by 10 to get the inference time for this mobile net V2 on the current SL2610 SoC. So, and we can track the duration, the curve for a number of metrics. So the total duration, the execution on the hardware, the execution on the CSS. So it's very useful to understand when there is a regression. For example, if suddenly we have a pattern matching that is failing and the operation is falling back to CSS or to host, we will have a spike in performance. So we will detect that automatically. And we also have support for Perfecto visualization. So we are using the standard Perfecto web tool to profile the model that we compile. So we have two kinds of profiling, one for what is done at compile time, where we can see for the detail of the execution of each and every operation. And we have also a runtime profiling, which measure the actual execution on the hardware. Maybe if that is interesting and we have time, I can give some demo of the dashboard. I can present some of the results that we have today on the dashboard and the Perfecto tool. Okay, now I'm going to talk about a bit about the current architecture and the challenge that we met over the development of the Torq compiler. So initially we started, and Max here in the school knows that very well. We started with direct TOSA to Torq HL conversion. So the LINALG, the lowering from TOSA to LINALG was really overwhelming. It looked very, very difficult to pattern match this kind of operation and convert that to our own dialect. So we create this Torq high-level dialect. So we have a number of Torq HL dialect for convolution, for matmul, for basically all the operation that we can support at the lowest level of the hardware. But it was really, we thought it was really too hard to do the conversion from LINALG. So we started with TOSA because our hardware basically was matching more or less the capability of TOSA. So that was easy. But then while doing that, we had to develop our own tiling algorithm, which we call now Torq HL tiling, and it was limited to single operation. So we had to evolve. Actually, this is what I'm talking about here in the second section. So now most of our pattern matching is done starting from LINALG, not TOSA. But just to come back to the initially what we had, so beside the conversion, we also program our kernels, so with quite low level and difficult to maintain hardware API, which we call MDL. So we had a lot of difficulty for the conversion from TOSA or Linalg, and then the creation of a kernel that can support any number of parameters in the operation that we support. For example, all the convolution parameters that are defined in TOSA. We have a quite fat and complex serialization code and very weak RISC-V and host integration for the CSS and host flowback. So fast forward to now, as I said, we support most of the operation in Linalg, which we convert to Torq shell. We have created a number of passes which will optimize Linalg for Torq execution. So instead of doing the optimization or the manipulation of the operation as part of the conversion, we first optimize the Linalg. We decompose some Linalg operation into other Linalg operations. We stay in pure Linalg before conversion. We have a quite complex compute constant path, which is simplifying the model quite significantly, optimizing it. And then we also, as part of this Linalg optimization path, we developed a number of BF16 decomposition of operations. Decomposition of BF16 operation, including softmax, earth, 10H, sigmoid, exponential, etc. So the idea is that when we try to, when a math operation is not supported by the hardware, we decompose it into a smaller operation which can run on the hardware through multiplication, activation, table lookup, this kind of stuff. A lot of effort went into tiling. So tiling fuse is the algorithm that we use. We are using the generic tiling interface for that. It's quite complex, but it's starting to work very well. We develop also an easy kernel API, which express the loop capability of the hardware in a very easy and maintainable way. So now most of our low-level kernel migrated from those low-level NDL kernels to this easy kernel API. And then we developed this automatic LLVM CPU fallback for Coral NPU and host. So we don't have to do anything. Basically, everything is handled completely by IREE and LLVM project for us. Now to the future. So yeah, even for the next release, the compiler will not be able to compile any model. We will still have cases where the automatic fallback to CSS or host will not work. So that's why we need this executor discovery tool, which will run on top of the compiler. But eventually, we want to get rid of that. We want the compiler really to not fail and to compile any model. So that's what we want to focus on in the future. I think that's the end of my presentation. So if you have any question, I'm happy to answer them. Otherwise, I can also show some of the dashboard results that we have. Sven?
Yeah, I'm wondering if you are planning to do some quantization as part of your compiler. I mean, you support int 8 and 16 brain float, but maybe integer operations are much faster.
That's yeah. Actually, I know. So quantization, we don't want to reinvent the wheel, really. We'll use whatever is developed upstream. I know, for example, for stable HLO is supporting quantization, and it is, I mean, post-training quantization, and it is similar to what Light RT is doing. I think integrating support for this kind of method within the compiler makes a lot of sense. We do some kind of quantization in the sense that we can convert, for example, an FP. We have a conversion pass which will convert FP32 to BF16, also in64 to in32. So this is also something that we support. Now, regarding LLM-like quantization, like those Q4, Q8 that Llama CPP is doing, maybe we are investigating that. Maybe it makes sense to implement this kind of block quantization, but quantization as it with a training that with a quantization data set, I don't think we will do that. Yeah.
Thanks.
Any other questions? Okay. So maybe, yeah, just showing what we have in GitHub today. So that's the main Git project for compiler. We have the same diagram that I showed. We enabled the ticketing, so GitHub issue, but to be completely honest, we are a bit behind here. We don't have many tickets, but it's probably because we didn't animate that up to now. We want to support. We have a lot more customers now, and we'll have, I hope, more academic and enthusiast user of the Torq compiler. So I hope that we will see more ticket happening here, created here. So as I said, we have our own fork for IREE. So today we are using a branch which we call Torq 310, which is on top of the IREE 310 tag. We have quite a few patches on top, right? I think maybe it's maybe 20 patches, which we need to review and see if it makes sense to upstream them. So something for LLVM project and Torch MLIR. I wanted to show you a bit about. So this is the dashboard that we have. For example, in the case of MBV2, you can track the performance over time through multiple metrics. So it can be, for example, the DMA time or the total time or something else. You can view the perfecto trace for the runtime in FPGA. It is not very useful here because how runtime will execute all the operation that you see here in one run. So we don't rely on the CPU to execute those layers. So it's only one dispatch running all the layers within the model. But we want to we have also the compile time profiling. I think I have an example here. So this is a compile time typical compile time profiling where you can go in detail and look at what is happening for each of the operation. So you can really zoom in and look at the details of, for example, here we have a matmul. Yeah, it's very useful to understand what's going on if there is an issue of bandwidth between the DDR and if we are memory bound or compute bound, if there is anything to optimize in the execution to run on the NSS or the CSS or the host, it's kind of tough. I think that's about it. I don't know if you have any questions.
Let's give it a few more seconds if someone comes up with a question.
Okay.
So Abdel, I wanted to ask how the release cadence we have in IREE and like the way we do releases work for you, because I think we converge on releasing, I think every like 6 weeks or so, and we do both tags in the repo and also artifacts on PyPy.
Right.
So I wanted to ask how this works for you, and if there would be something we can make easier for downstream to work with.
I think it works well. So it took us a lot of time to upgrade to this 310. It took us 6 months basically, because we were focusing on making things work. But now that we have migrated to 310, I think the next, I mean, we had a lot of issues because TOSA did a major upgrade. A lot of things were, a lot of API changed in IREE and MLIR. So it was really a big upgrade. But now I think we want to track very closely the IREE developments. We already have a Torq 311 branch. So it was really straightforward to cherry pick all the batch that we have on top of the 310. So hopefully it will be straightforward to track the development. We plan to always base the release on the latest IREE tag, but as I said, we want to also make sure that we will capture any regression that happens in the main branch. I don't see any issue really. Okay. So I hope it was interesting to you guys.
Thanks very much, Abdel, for the presentation, and it was amazing to see all the demonstrations, like in depth, especially the dashboard breakdown and the profiling was very cool.
Cool. Thank you.